Imagine standing in a place where gravity seems to defy the laws of physics. From mysterious areas where cars roll uphill to bizarre spots where objects float in midair, there are some places in the world where gravity doesn't seem to work as it should. But first, we need to understand what gravity actually is. What is gravity? Put simply, gravity is one of the most fundamental forces in the universe. It controls everything from the movement of planets, stars, galaxies, and even the trajectory of light. Even though it is the weakest of the four fundamental forces of nature, gravity's effects can be felt over vast distances, and it influences the behavior of all objects with mass. It's what keeps the large-scale structure of the universe together, and it keeps the planets in orbit, and it's why we remain firmly on the ground. But there are a number of things that affect how strong it is. Let's talk about the basics of gravity. Gravity is defined as being the force of attraction between two masses. The larger the mass of an object, the greater its gravitational pull. Isaac Newton was the first to mathematically describe gravity in the 17th century with his law of universal gravitation, which states that every mass exerts an attractive force on every other mass. And while Newton's law describes how gravity works, it really doesn't explain why it works. And this revelation will only be made hundreds of years later by Albert Einstein's general theory of relativity, which was published in 1915. This shows that gravity isn't a force in the traditional sense, but instead something that's the result of the way that space and time curve around massive objects. Einstein said that massive objects like planets and stars distort the fabric of space-time, and they create a well that other objects can fall into. Smaller objects like spacecraft or human beings move along the curves in this warped space-time, which we perceive as gravitational attraction. For example, the Earth orbits the Sun, not because the Sun is pulling it with a force, but because the Sun's mass curves space-time in such a way that the Earth follows a curved path around it. The best way to think about this is by imagining a heavy ball placed on a stretched-out sheet of fabric. The ball will create a dent around it in the center, and smaller objects, when they're rolled onto the fabric, will move towards the ball because of the curved surface. It's this theory that also predicts strange phenomena like gravitational time dilation, where time moves slower in stronger gravitational fields, gravitational lensing, where gravity can bend light, and the existence of black holes, where gravity is so strong that not even light can escape. How about some things that affect gravity? Well, there are 6 main factors that will determine how much of an effect that the gravitational force from an object will have on something else. One is mass. The more massive an object is, the stronger its gravitational pull. So for example, the Sun, which has about 330,000 times the mass of the Earth, exhibits a much stronger gravitational force, and this is why the planets in our solar system orbit around it. Similarly, black holes, which pack enormous mass into a very small area, have gravitational pulls so intense they can trap light. On Earth, gravity is responsible for the weight that we feel, as our weight is the product of the way gravity interacts with us. This is why if we set foot on Mars, where the gravity is weaker, we would weigh less. Number 2 is distance. The further two objects are away from each other, the weaker the gravitational force is between them. This is because gravity follows what's known as an inverse square law, and this means that if you double the distance between two objects, the gravitational force between them is reduced fourfold. This is why astronauts in orbit, such as on the International Space Station, will experience microgravity because they're far enough from Earth's center that the gravitational pull is much weaker, but it's not gone altogether. 3 is the distribution of mass. The way that mass is distributed within an object can also influence gravitational effects. A spherical object like a planet has a gravitational field that acts as if all the mass were concentrated at its center. In reality, though, this mass is unevenly distributed, such as in mountains, ocean basins, or underground structures. And in these places, there can be local variations that are known as gravity anomalies. It's this factor that explains most of the fluctuations in gravity on Earth. 4 is the rotation. The rotation of a planet can affect how gravity is experienced on its surface. For example, Earth isn't a perfect sphere. It bulges slightly at the equator because of its rotation. As a result, gravity is slightly weaker at the equator than at the poles because the objects at the equator are farther from the planet's center. Further to this, the centrifugal force that's caused by the Earth's rotation slightly counteracts gravity at the equator and reduces the gravitational force that's felt there even further. Number 5 is tidal forces. These tidal forces happen because of the difference in gravitational pull that's being exerted by one object on different parts of another. For example, the Moon's gravitational force on the Earth is what causes tides, as the side of the Earth that's closest to the Moon experiences a stronger gravitational pull than the side that's farthest away from it. In a similar way, as well as holding the Moon in orbit around the Earth's gravity exerts tidal forces on the Moon. This causes its rotation to synchronize with its orbit, and this is why we always see the same side of the Moon when we look at it. Number 6 is relativistic effects. While it's not something that we experience, or at least perceive from the Earth, in a very strong gravitational field, time slows down and space is curved. These effects are most clear near massive objects like black holes or neutron stars. For example, near the event horizon of a black hole, gravity is so strong that space-time becomes infinitely curved, and any object falling into it will appear to freeze in time from the outside if you're looking at it. If you happen to be the object that falls into the black hole, time in the rest of the universe will appear to speed up, and you'll see billions of years pass in a flash. Let's talk about gravity on the Earth now. There are, then, various different places where gravity can be shown to be working slightly differently on Earth, and these can be split into two different categories: those where gravity is actually stronger or weaker than normal, and those where, for completely different reasons, there's the illusion that gravity has completely stopped working. Let's take a look at places where gravity actually works differently. Mount Nevado Huascaran in Peru. Mount Nevado Huascaran is in the Cordillera Blanca range of the Peruvian Andes, and as well as being the highest mountain in Peru, it's also the highest point in the tropics with an elevation of 22,000 feet, or just over 6,700 meters above sea level. This combination of height and its position mean that it's a place where gravity can noticeably be measured to behave slightly differently from what we experience at sea level. The peak of the mountain is so far from the center of the Earth that according to the inverse square law of gravity, the gravitational pull will be weaker than at lower altitudes. This works in combination with the fact that the mountain is close to the equator, and as the Earth bulges around the middle, it puts the peak even further away from the center than an equal height mountain would be somewhere else. This all means that Nevado Huascaran has some of the weakest gravitational pull on Earth, and a person standing at the summit would weigh slightly less than they would at sea level. Scientists have calculated that the gravitational acceleration here is around 9.76 meters per second squared, which is just a little less than the 9.8 meters per second squared that we experience at sea level. But this is still enough to be classed as an anomaly. As well as making us lighter, objects fall slightly slower at the top of this mountain compared to lower altitudes, and interestingly, the reduced gravitational pull also means that the internal systems of our bodies, including our cardiovascular and respiratory functions, respond differently here at these altitudes. Combined with the low oxygen levels at these heights, this is why climbers experience an increased strain on their health. They must carefully acclimatize to the environment. Hudson Bay in Canada. Covering an area of 470,000 square miles, or over 1 million square kilometers, Hudson Bay, which is in northeastern Canada, is a huge geographic feature that's been important for local communities for thousands of years. More recently, though, scientists have discovered that it's also the site of a gravitational anomaly, and to begin with, no one had any idea why. It was found that in this region the force of gravity is slightly weaker than in other parts of the world, and while the difference is tiny, seeing a reduction of 0.015% is still significant enough to have drawn the attention of geophysicists, looking to explain why gravity is behaving differently in the Hudson Bay area. Following an extensive study, the gravitational anomaly is now mostly thought to be down to two main factors: post-glacial rebound and the presence of the Laurentide ice sheet during the last ice age. These geological events were crucial in the formation of this region's landscape, and they've left a long-lasting effect beyond what you can see. Post-glacial rebound is the name that's given to a slow process that sees the Earth's crust rise after being crushed under the weight of massive ice sheets. Most of Canada was covered during the last ice age, which ended around 10,000 years ago, and the Laurentide ice sheet, which was one of the largest, was about 2 miles thick in some places, which would have exerted a huge amount of pressure on the Earth's surface and caused the crust to sink. When the ice melted, this pressure was relieved and the Earth's crust began to slowly recover. This process, however, is still ongoing, and the crust has not yet fully returned to how it was before the ice age. This slow rebound creates a subtle but measurable difference in gravity because the mass of the Earth beneath Hudson Bay is still displaced compared to other regions. The Laurentide ice sheet had another major effect on the region too, because it displaced a huge amount of mass from Hudson Bay. When the ice melted, it left behind an area that is less dense than surrounding areas. This difference in density affects the distribution of Earth's mass, and as a result, the gravitational pull. Essentially, the gravitational force in Hudson Bay is slightly weaker because there's less mass beneath the surface compared to other parts of the planet. Alright, how about Chimborazo in Ecuador? If you were asked where the farthest point on land from the center of the Earth is, most people would probably guess the peak of Mount Everest because it's the tallest mountain in the world. Well, due to our planet's shape though, this isn't actually correct, and the true answer is the little-known Mount Chimborazo, which is in the Andes mountain range of Ecuador. Standing at a height of 20,548 feet or 6,263 meters, Chimborazo has become, as a result, an interesting place to study how gravity varies across the globe. The Earth isn't a perfect sphere, but what's known as an oblate spheroid, where it bulges slightly at the equator and is flattened at the poles. This bulge is caused by the Earth's rotation, meaning that locations near the equator, like Chimborazo, are far from the Earth's center compared to places at higher latitudes. The effect makes such a distance that, despite being around 8,500 feet or 2,600 meters shorter than Mount Everest, the peak of Chimborazo is actually around 6,500 feet or 2,000 meters further away from the center of the Earth. This increased distance from the Earth's center at Chimborazo's summit directly affects the gravitational force that's experienced there. Again, because of the inverse square law, studies have shown that the gravitational acceleration up there is about 9.763 meters per second squared, compared to the average of 9.8 meters per second squared. And that would be enough to make you weigh slightly less and put some added pressure on your body to function in the same way as it does at lower altitudes. Chimborazo's gravity anomaly is important to know about and to measure for researchers in the field of geodesy, which is the science of measuring the Earth's shape, gravity field, and surface. They can use the data from places like here to refine models of the Earth's gravitational field, which is important for our satellite navigation, geophysics, and understanding the planet's internal structure. Bangui in the Central African Republic. Bangui is the capital of the Central African Republic, but it's also home to one of the most difficult to explain gravitational anomalies on Earth. Known as the Bangui gravity anomaly, it's a region where gravity behaves unexpectedly, with a stronger gravitational pull than would otherwise be expected based on the area's landscape. This anomaly has been a mystery for some time, and while its exact cause remains uncertain, there are several theories about why gravity is different here. It was first detected through satellite-based gravimetric measurements and ground-based studies, which revealed that the pull here in this area is significantly higher than in surrounding regions. There aren't any of the geological formations you would usually look for in cases like this, like large mountains or dense rocks, and it's particularly surprising because the region around Bangui is relatively flat and geologically stable. There are no major tectonic plate boundaries, significant volcanic activity, or dense mountain ranges that would usually be linked with a heightened gravitational force. The leading theory right now for this anomaly is that the area might sit on top of a previously undiscovered and completely buried impact crater, which could have been caused by a large meteorite strike that happened millions of years ago. Meteorite impacts compress materials in the Earth's crust and would result in a concentration of denser rock materials beneath the surface. This theory is supported by the fact that the anomaly is circular, which is consistent with the shape of impact craters elsewhere found on Earth. While there's no visible crater at the surface, erosion and sedimentation over millions of years could have concealed the original impact site, leaving only the gravitational anomaly as evidence. Another possibility is that the anomaly is caused by dense rock formations deep beneath the Earth's surface. These could be what remains of ancient geological processes such as the uplifting or folding of the crust, which left behind unusually dense materials in the region. This would account for the higher gravitational readings too. And lastly, there's also been the suggestion that this anomaly could be related to mantle plumes or variations in the Earth's mantle, where hot, less dense material rises towards the surface and has complex interactions with the surrounding rock. This explanation is seen as less likely though, because mantle plumes are usually associated with volcanic activity, which is not present in this region. Let's take a look at the Indian Ocean gravity anomaly. The Indian Ocean gravity anomaly is another one of those more mysterious gravitational ones on Earth. It's found in the central part of the Indian Ocean. This region has an unusual deviation from the expected gravitational field, where gravity is significantly lower than it should be. This anomaly is found south of the Indian subcontinent and north of Antarctica, and it covers a large area of the ocean where the gravitational pull is weaker than in the surrounding regions. It's an area where the Earth's gravitational field dips by more than 100 milligals, which is a unit used to measure gravitational variations compared to what would be expected based on the local topography. Essentially, something below the surface is creating a lack of mass or a different distribution of mass than geologists and physicists would normally expect. Still, no one knows for certain what's causing this, but there are several theories. The most likely explanation is seen as having to do with mantle dynamics. The Earth's mantle, which lies beneath the crust, is constantly moving because of the heat from the planet's core, which causes convection currents. These currents can create upwellings and downwellings of material that are denser or less dense than the surrounding mantle. In the case of the Indian Ocean gravity anomaly, the theory is that a large, low-density region deep in the mantle is creating the gravitational dip. Another suggestion is that the anomaly is caused by the remnants of ancient tectonic plates or subducted slabs of oceanic crust that have sunk deep into the Earth's mantle over millions of years. These sunken slabs could have altered the mass distribution below the surface and affected the gravitational field above. Some scientists think that the remains of ancient Tethys Ocean Plate, which moved beneath the Eurasian Plate, might still be within the Earth and contributing to the anomaly. Because of the potential to learn more about the Earth's mantle, the Indian Ocean gravity anomaly continues to be an area of active research. Modern satellite technology, such as data from the Gravity Recovery and Climate Experiment mission, has provided more detailed insights into the Earth's gravitational field here, allowing scientists to map the anomaly with greater precision, and hopefully one day be able to explain it. The Great Rift Valley in East Africa. The Great Rift Valley is one of the most geologically active regions on Earth. It's known for its tectonic activity and stunning landscapes. It covers a distance of 3,700 miles or 6,000 kilometers from northern Syria to central Mozambique. In the future, it's expected to form an ocean in the middle of Africa, and those extreme forces are not only affecting the geography of the region, but also the gravity that's experienced there. This rifting process, which has been shaping the region for millions of years, involves the gradual movement of tectonic plates as the African plate splits into the Somali and Nubian plates. This is creating enormous cracks and depressions in the Earth's surface, along with volcanic activity and seismic events, and as a result, the Great Rift Valley has a unique distribution of mass beneath the surface. One of the most important factors that contribute to the lower gravity in parts of the Great Rift Valley is the presence of the Rift Valley and deep depressions. These low-lying areas, such as the Danakil Depression in Ethiopia, are formed as the Earth's surface stretches and sinks. The reduced mass in these valleys leads to a weaker gravitational pull, and things are then made more complex by volcanic activity. Interestingly, the gravity in the Rift Valley doesn't behave the same across the entire region. While many parts of the rift experience weaker gravity, there's also areas where gravity is slightly stronger, such as the Ethiopian highlands and Mount Kilimanjaro. The South Atlantic Anomaly, or SAA, is a region where the Earth's magnetic field is significantly weaker compared to other areas, stretching from South America to the southern Atlantic. This anomaly is mainly known for its effects on our planet's magnetic field, but it also has connections to gravitational variations in the area. It's a region that's become important because it impacts the operation of satellites, space missions, and even on the International Space Station, where astronauts experience increased exposure to cosmic radiation as they pass by. The weakened magnetic field in the SAA is caused by complex interactions with the Earth's core. Earth's magnetic field is generated by the motion of molten iron and nickel in the outer core, which is a process known as the geodynamo. And over time, this process can create regions where the magnetic field is weaker, as is the case with the South Atlantic. The SAA is an area where the inner Van Allen radiation belt, which is a ring of charged particles in space that are trapped by Earth's magnetic field, comes closest to the Earth's surface, exposing satellites and spacecraft to higher levels of radiation. As a structure beneath the crust is enough to affect the magnetic field, then maybe it's no surprise that there are gravitational anomalies too. In the South Atlantic, some studies have suggested that these could be related to mantle convection, where this convection current of molten rock in the mantle caused variation in the distribution of mass beneath the Earth's surface. But the SAA region doesn't have large changes in gravity like some other locations like the Hudson Bay gravity anomaly or the Great Rift Valley, but scientists have detected small variations in the gravitational field using satellites. Researchers think that this could be linked to the South Atlantic tectonic plate and its interaction with the surrounding plates. Most of the tectonic plates can cause changes in the density of the Earth's crust, which in turn leads to small variations in the gravitational field. As well as this, the slow movement of molten material in the mantle beneath the SAA could be influencing both the magnetic field and the gravitational anomalies. The Chicxulub crater, which is on the Yucatan Peninsula in Mexico, is one of the most important geological features on Earth because of its connection to the mass extinction event that wiped out the dinosaurs around 65 million years ago. The enormous impact crater, with an estimated diameter of around 93 miles or 150 kilometers, was formed when a massive asteroid, which was believed to have been around 6 to 9 miles or 10 to 15 kilometers in diameter, collided with the Earth. The Chicxulub impact is widely seen as the primary cause of the Cretaceous-Paleogene extinction event, which led to the extinction of roughly 75% of Earth's species, including non-avian dinosaurs. It's obviously then a huge, historically significant place, but studies have shown long-lasting effects of the impact too. As the Chicxulub crater also has some interesting gravitational anomalies. After such a massive event, the area around the crater shows measurable variations in gravity due to the differences in density. Studying the Chicxulub impact crater isn't easy. After tens of millions of years, it's now buried beneath layers of sediment. In fact, gravitational measurements are one of the most effective tools to fully understand its structure. After an impact of such magnitude, the distribution of mass in the Earth's crust was changed, and this has created areas with both higher and lower gravitational forces. Within the Chicxulub crater, there is a noticeable negative gravitational anomaly at the center of the impact site. This means that gravity is slightly weaker. The asteroid's impact displaced massive amounts of rock and created a central depression filled with less dense, fractured, and melted material. These materials are less dense than the solid, undisturbed rocks surrounding the crater and are what have resulted in a weaker gravitational pull in the region. Around the rim of the crater, though, there's a positive gravitational anomaly where gravity is stronger. As the asteroid hit, it caused a rebound effect which created a raised ring of dense material around the outer edge of the crater, and it's this ring, which is known as a peak ring, that contributes to the stronger gravity in that area. The South Pole in Antarctica is one of the coldest and remote places on Earth, and while it's mostly known for its role in the planet's magnetic field, it does have some unique gravitational characteristics too. Found at the southernmost point of Earth, these differences in gravity are the result of a combination of factors, including its location on the planet, the thickness of the Antarctic ice sheet, and the shape of the Earth itself. At the South Pole, gravitational acceleration is around 9.83 meters per second squared, compared to the typical 9.8 meters per second squared at sea level elsewhere on the planet. It is a small difference, but it means that you would weigh slightly more at the southern pole, and there would be a slight effect on your body's cardiovascular system. Another thing that affects gravity at the South Pole is the Antarctic ice sheet, which is the largest ice mass on Earth and contains around 60% of the planet's fresh water. The sheer volume of ice creates a gravitational anomaly because of the massive amount of frozen water. It adds significant mass to the region. More mass means a stronger gravity, so gravity here is slightly stronger than it would be. Interestingly, the continual melting of the Antarctic ice sheet due to a bit of climate change is already having a measurable impact on local gravity. As the ice melts, the mass of the ice sheet decreases, and the gravitational pull in the region is gradually weakening. But the South Pole too also has minor gravitational anomalies because of the behavior of the Earth's crust and mantle in that region. Beneath that thick ice sheet lies a complex structure, including mountain ranges, subglacial lakes, and variations in crustal thickness, all of which influence local gravity. Areas with denser rock formations or thicker sections from the Earth's crust exert a slightly stronger gravitational pull, while regions with less dense materials create weaker gravitational fields. Now let's take a look at places where gravity is an illusion. The reverse waterfall of Nanagat, India. So the reverse waterfall at Nanagat in India is a natural phenomenon that, at first, appears to go completely against how you'd normally expect water to behave under the force of gravity. The site attracts visitors from all over the world who come to see the water flowing upward rather than cascading downward. While it might look as though gravity is reversed here, the reverse waterfall is, however, an optical illusion created by the local landscape. Nanagat Mountain Pass was historically used as a trade route between the Konkan coast and the Deccan Plateau, and it's long been a popular place for its scenic views. During the monsoon season, the Western Ghats experience heavy rainfall, and countless waterfalls begin to flow over the cliffs and hillsides in the region. And it's during this time, between June and September, that the reverse waterfall can be observed at its best. The reverse effect happens when strong winds from the monsoon season blow up the steep cliffs with such force that they're strong enough to counteract gravity and push the falling water upward. This doesn't happen everywhere, of course, and the reason why is the particular landscape here funnels the wind through the tight spaces and up the vertical cliffs, generating the upward draft needed. The water also helps with this, as it's already falling at a slower rate because of its relatively low volume compared to larger waterfalls, and it's more easily caught by the powerful wind. The reverse waterfall effect, though, is most pronounced during the peak monsoon season when both rainfall and wind speed are at their highest. During this period, the waterfall produces fine mist and droplets, which can be blown far back into the air, making it appear as though a waterfall is suspended or flowing in reverse. How about the Mystery Spot in California? The Mystery Spot in Santa Cruz, California is one of the most famous roadside attractions in the US, and it's known for its unusual optical illusion. Located in a redwood forest, the area is just 150 feet or 46 meters in diameter, but has completely baffled people ever since it first opened to the public in 1940. It's described as a place where the laws of physics and gravity seem to operate differently, creating a series of strange effects that leave people questioning what they see and feel. As you enter the Mystery Spot, you straightaway notice that something feels off. People standing upright appear to be leaning at strange angles, and balls seem to roll uphill. As visitors walk around, the world around them seems to tilt and their sense of balance is thrown off. Even objects like chairs or table appear to defy gravity, making it hard to tell which direction is truly up. The main attraction here at the Mystery Spot is a tilted cabin, where the effects are clearest to see. Inside this cabin, people seem to be able to stand at angles that would normally cause them to fall over, and it feels like they're being pulled sideways. For many visitors, simply walking through the cabin makes them feel dizzy, their bodies struggling to make sense of the visual information they're receiving with their own sense of balance. While the effects at the Mystery Spot may feel supernatural or mysterious, they are of course the result of cleverly made optical illusions and the site's unique construction. The entire area is built on a steep hill, and the tilted cabin is built at an angle that confuses visitors' perception. As a result, the brain misinterprets visual cues about the angles and slopes, making people feel as though they're leaning or standing at impossible angles. Over the years, though, not everyone has looked for the simplest explanation for what happens here, and have instead put forward other ideas about what makes it such a mystery spot. Some have believed that it's a true gravitational anomaly or underground geological formations, like deposits of iron ore or even alien activity, are responsible for these strange effects. The Mystery Spot remains a popular tourist destination, as it's been there for more than 80 years. Part of its charm comes from its playfulness, and the same way we like to watch magic shows, we all enjoy trying to make sense of what we see and feel, all while being entertained by the seemingly impossible things happening before our eyes. The Magnetic Hill in Ladakh, India, is one of the region's most mysterious natural phenomena, and is one of only a handful of gravity hills around the world. Found at an altitude of 14,000 feet or 4,300 meters, this hill has confused visitors for years with its ability to make vehicles appear to roll uphill against the force of gravity. And because of this, some have believed there's a strange magnetic force at work, although of course there's a much simpler explanation. Those who visit will find that when vehicles are left in neutral at a specific spot on the road, they appear to roll uphill. People often park their cars or bikes at the marked spot and watch as the vehicles start to move, apparently defying the laws of physics. Tourists traveling through here will usually make it a point to stop here at the Magnetic Hill to see it for themselves, with it now having become one of the most popular attractions in the regions. Local myths and legends have also added to the mystery of the place, with stories that the hill is a gateway to heaven, and only those destined for paradise can ascend the hill effortlessly. Unfortunately, the truth is far less exciting, as Magnetic Hill is not actually magnetic, and there are no mystical powers, and it isn't evidence for alien activity. Instead, it's the result of an optical illusion that's caused by the natural landscape surrounding the hill. The layout of the region creates the impression that what is actually a slight downhill slope is instead an uphill one. The horizon and surrounding hills create a visual frame of reference that tricks the brain into perceiving the slope incorrectly. In reality, the road at the Magnetic Hill is gently sloped downward, but because of the positioning of nearby mountains and the way that the road curves, it appears as though the opposite is true. The illusion works because humans rely so heavily on visual cues for our spatial orientation that when they're misleading, like when the horizon is hidden or distorted, our brain misinterprets the actual slope of the road. The Hoover Dam on the border between Nevada and Arizona in the United States is another piece of incredible engineering, and it's become a treasured national landmark. It was built during the Great Depression, helping thousands of people return to work, and it was completed in 1935. It is an enormous structure across the Colorado River, and it's created Lake Mead, which is the largest reservoir by volume in the country. The illusion here works best when you're standing at the top of the dam, and from there you can do a simple experiment. Either pour some water across the side or drop a lightweight object. What you'd expect to see is, of course, for it to fall, but when conditions are right, the opposite will happen. The sight of water droplets or lightweight materials floating up into the air creates the illusion that the Hoover Dam has somehow created a gravity-defying effect. This, of course, is not the case, and what seems like gravity behaving unusually at the Hoover Dam is in fact an effect that's caused by the strong updrafts that are created by the dam's architecture and the natural environment around it. The curved structure causes the air to flow in specific patterns, so as the wind moves through the narrow canyon formed by the Colorado River and hits the face of the dam, it's forced upwards in powerful currents. These updrafts are so strong they can push lightweight objects and water droplets upward, counteracting the downward pull of gravity for a moment. For visitors, this gravity-defying illusion is a memorable part of Hoover Dam experiences, and many tourists enjoy testing it out by pouring water from a bottle or dropping a feather or piece of paper. It is important to point out, though, that this only works with lightweight material, and if you drop something heavier like a coin or a rock, that won't work for that effect, but it will probably get the attention of the security there. Alright, let's bring it all together. Gravity is one of the most important forces in the universe, and it's the reason our sun, our solar system, and our planet are able to form in the first place. On an individual level, it's also what keeps us on the ground and gives a predictability to the way that things work in our day-to-day lives. This doesn't mean it's an absolute constant, though, and while big examples of gravity working differently come from places that are too far away to really matter to us, like in black holes or on other planets, there are fluctuations and changes that we can see here on Earth. Space technology, for example, relies on a full understanding of gravity to remain in orbit, and the systems in our bodies have evolved to function within a very narrow tolerance. By studying gravitational anomalies around the world, we're able to get a much better idea of how likely it is for the Earth's forces to change in enough of a way to impact our lives. From little understood processes in the Earth's mantle to how climate change has been shown to be changing gravity, and even using gravitational measurements to peer deep into our planet's surface to detect structures like impact sites. It shows just how important to our lives gravity is, that places where even the illusion of it working differently become such popular visitor destinations, with it usually being such a given that it works all the time, and that virtually everything we do relies on its continual presence. Thanks for watching, everybody. I'll see you next time. Thank you to our channel members.